Good day to all of you. So we're already in the tutorial of doing Hamming code for single error correction. So actually, this Hamming code solution is based on William Stallings Computer Organization and Architecture 10th edition, specifically in Chapter 5, Internal Memory. So before I start my tutorial, I have to say that if you have any other solutions, a Hamming code shortcut, the important thing is the results are the same. So let's start the tutorial. So as you can remember with our discussion, we have figure 5.10. So that's the illustration in chapter 5 in which there is a word stored and then it is fetched and there is a single error within the specifically 12 bits of word. So for this, so as you can remember, the word is, okay, so the word specifically is 0011 and then 0100 and then four ones, 1111. And then specifically the error is in, okay, so let's indicate the error. The error is where? It is specifically located in D3. So for Hamming code, since the values are zeros and ones, so the original value for D3 is 0 and then it becomes 1. So how are we going to know? Of course, we know the bit position, but how are we going to prove that that bit position has the error for Hamming code? So before that, we're going to create a table as illustrated in 5.10, but for the knowledge of how to do it, how to derive, so that you can derive it on your own. Okay, so we have this bit position. Okay, we have bit position. So since this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have, okay, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And then we have this position number. Next, the next value in the table is the position number. So what is this position number? This will be very important for the operation later that we're going to do. Why? Because we're having these values so that you can remember. Okay, so position number is the binary number equivalent of this 1 to 12. So let's start with 1. Okay, so for 1, so for you to know the values if you have digital electronics background, so we're the weights of the values is we have for per digit is 1, 2, 4, and 8. Okay, since we have 12 bits, meaning um, 12 is the maximum number, it will fit for 4 digits. So we have for 1 is we have 0001. Okay. So we have 001. Okay, why it's 001? It's because of 1, 2, 4, 8 values. So we have, since this is 1 and this is 1, so that is 1. And the next, as you can get it, and next is we have 2. So 2 is 0010 because in the positioning, the value of the second digit is 2. And then we have 3, 0011 because 1 plus 2 is equal to 3. Then 4 is 0100. And then 5 is 0101. So we have 4 plus 1 is equals to 5. And then 6 is we have 0, 1, 1, 0. 4 plus 2 is equal to 6. And then 7 is 0, 1, 1, 1. So 4 plus 2 plus 1 is equal to 7. And then next is we have 8. We have 1, 0, 0, 0. So that's the position, the last bit. The most significant is 1. So that's 8. And then 9. 1, 0, 0, 1. 8 plus 1 is equals to 9. And then 10 is 1, 0, 1, 0. 8 plus 2 is equal to 10. And then 11 is 1, 0, 1, 1. 8 plus 2, 10 plus 1 is equals to 11. And last but not the least is we have 12, 1, 1, 0, 0. So that's why that's the derived, that's the number, equivalent number, binary number rather, of this bit positions 1 to 12. So this is where you derive the values. If you have background with binary numbers, it's easier for you. But if you're not yet familiar with binary numbers, just use this values for the positions of four digits: 1, 2, 4, 8. And then there are powers of 2. What if it's 5 digits? So next to 1, 2, 4 times 2 is 8, times 2, 16, times 2, 32. Just multiply it always by 2. So that's the position number. And then we have the next is we have the data bit, and then we have the check bit. So it is said it's easier for check bit. So for check bit is you have the check bit should be the values which are powers of 2. So which of them is the power of 2? As you can see here, this is already the power of 2. 1, 2, 4, and 8. So let's put them with a label. We have C sub 1, C sub 2, and then C sub 4 is C4 rather, and then we have 8 is C8. So as not you for you to be confused. And then the remaining values, these are the data bit values. So those don't have any labels yet. So for 3, we should have D1. And then for 5 is we have D2. And then 6 is D3. And then we have 7 is D4. And then 9 is D5. And then we have 10 is D6. And then 11 is D7. And then 12 is D8. Okay. And then let's assign the values. So the original values is by means of the actual direction. So we have 0, 0, 1, 1, 0, 1, 0, 0, and then 1, 1, 1, 1. And then it is said that the error is in D3. So where is D3? So this is D3. So this should be the error from 0, it becomes 1. So how are we going to prove that that data bit has the error? So first is we're going to produce the check bit of the original value. So what is the check bit? So first is, okay, for C1, okay, so let's write it for C1. Okay, since C1, as you can see here, with our value here, C1 should contain the data bits with 1 in the uh, position number. So, okay, let's disregard C1, C2, C4, and C8 because there are check bits. Okay, which of the data bits here has a value 1 on the position number? So, first is we have 0011. There's a 1 here at the rightmost, so it should be included. So, from C1, we have D1. And then next, Can we find another? Okay. Okay, D1. Okay. Does it have also a 1 here? Of course. So we should include D2. Okay, so we have D2. Okay, next. Another. So does D3, it doesn't have a 1, so we do not include D3. Next is we have D4. Okay, so we have D4. Okay, next. D4, then check bits is 8, then 9. Since this is actually an odd number, as you can see, almost odd numbers are included here. So we have D5, and then we have 10 is not included because it's an even number. So we have, next is we have D7. Okay, so we're going to get the value here is by means of XOR. So the operation here is XOR. I'm going to explain later um, the XOR. What's the operation of the XOR operation in binary? Okay, so that's an XOR. So we already get the checklist, check the for the C1. And then next is we have C2. Okay, we have C2. Okay, as you can see here for C2, it should contain a value 2. So which of these data bits are included? So we have 3. So it's also included in C2. So we have D1. Okay, next we have, so 4 is not included. So 5. So we have, okay, we have, 5 rather. Is 5 included? Actually not because it doesn't have a 2. So next is we have D3. Okay, we have to be careful. We have to check if in C2, 2 must also be included. Okay, so D3, okay, is D4, 2 is included, yes. So let's include D4. Okay, next is we have, okay, check, this is a check bit, and then it's not included. So we have next, we have a 2 here. So we have D6. Okay, so in 11, we also include it here. So we have D7. And again, the operation is XOR. Okay, XOR. Okay, XOR. Okay, next is we have C4. So for C4, just the same with C1 and C2, look for data bits which has a value 4 in its position number. So 4. So we have 5. So let's put corresponding for 5 is D2. And then, okay, D3 is also included because um, 4 plus 2. Okay, so we have D3. And then, is 7 also included? Yes. So let's include D4. And then, do we have 4? It's a check bit. And then 9 is not included. And then 10. Then 11. Okay, then 12. We have the sub D8. And then again, we have XOR. Okay, next is we have, last but not the least, is we have C8. Okay, C8. So, which data bits which contains a value 8? So, which of them is, okay, so 8 is we have, okay, so let's, because this is a smaller numbers, so let's start with number 9. So, number 9, we have D5. Okay, next is we have Okay, actually D5, D6, D7, D8 because all of them has 8 in their value. So we have D5, D6, D7, and D8. And then we have Operation XOR. So we've already completed the ones that we have to get the check bit. So what happens after this one? Okay, what we're going to do now is we're going to substitute the values of this D1, D2, D4, D5, these data bits into the original. Okay, the original, of course, we have to, this is the original value is 0 to get the check bit, and then another check bit if there is a change for this particular bit. Specifically, it is said it is in D3. Okay, so what are we going to do? So we have to substitute. So first is we have to substitute. Okay, so we have C1. So D1, what's the value of D1 is, okay, so we have 1. And then D2 is we have 0. And then next is D4. D4 is 1. And then D5 is also 1. And then D7 is 0. So that is our value. And then we will have XOR operation. So how does XOR operation works? So XOR operates as this is the table. This is the truth table for XOR. So we have 0, okay, 0, 0. Okay, wait. Let's just erase. Okay. So for XOR, we have 0, 0, 1, 1, 0, 1, 0, 1. And then for XOR, okay, so these are the values. Okay. Okay, what's the meaning of XOR? XOR means exclusive OR. So it means for XOR, for the value for it to be 1, the value of the two values must be different from each other. You can see if there are both 0, XOR is 0, or if they're both 1, it's also 0. So for you to have a value 1 for XOR, the input must be different. And then another characteristic of XOR is that you should do it pairwise. Unlike the other operations such as and or, they can be done simultaneously. How many binary numbers it is with and or operation. But for XOR, you must do it in pairs. So such as, for example, since this is our example for C1. So for you to evaluate XOR, you should this two to be paired, and then you should also pair this one, and then of course this is the fifth one. After doing the XOR here, and then you will have the value. So 1 XOR 0, since they are different, it is 1, and then 1 XOR 1, because they're the same, it is 0, and then these two will be paired. 1 XOR 0, 1, and then 1 XOR 0 is equal to 1. So C sub 1's value is equal to 1. Okay, next is we have C2. So C2, get the values, exact values. D1 is 1, and then D3 is we have the original value, okay? The original value is 0, and then D4 is 1, and then next is D6 is 1, and then D7 is 0. Okay. Okay, then again the operation is XOR. Okay. So again, um, evaluate it by pairs. Okay, so we have 1 XOR 0 is 1. So 1 XOR 1 is 0. Then 1 XOR 0 is 1. 1 XOR 0 is also equal to 1. So that is the value of C2. Okay, next is we have C3. Okay, C3. Okay, so next, C3. It's not C3. Okay, let's erase it. Okay, okay, let's just change it to C4. So I'm sorry for that. Okay, let's change it into, okay, C4. Okay, C4 is, okay, D2. D2 is 0. And then next is we have D3. D3 is 0. And then next is D4. D4 is 1. And then next is we have D8 is we have 0. Okay, and then the operation is XOR. Okay, so again, let's evaluate. Okay, so by pairs first. Okay, the good thing is these are by pairs. Okay, so we have 0 XOR 0 is 0, and then 1 XOR 0 is 1, and then 0 XOR 1 is 1, so the value is 1. Okay, and then last but not the least is we have C8. So C8 values are these 5, 6, 7, 8. So 5, 6, 7, 8. So we have 1, 1, 0, 0. Okay, and then XOR. Okay. Okay, so let's evaluate by pairs. 1 XOR 1 is 0, 0 XOR 0 is 0. So 0 XOR 0 is equal to 0. And then we're going to read after getting these values is we're going to read it upwards. And then the check bit is 0, 1, 1, 1 for the original value. Okay? So you have to remember this. This is the check bit for the original values without error. So how are we going to get the the error to prove that the error happens in D3? Okay, since we have already changed D3 from 0 to 1, we have to um, get the check bit of the word with the error. Okay, since the error is in D3, for shortcut, not to recompute it again, you have to look here which of the check bits here with the C1, C2, C4, and C8 that has D3. So as you can see, we have C2 and C4 only, which has D3. So we have to recompute it. Okay, so let's go back. So for C1, okay, for C1, it will be retained. The original value will be retained. We just have to compute the new value for C2. Okay, let's just copy the original, which doesn't have any changes. We have for D1 is we have 1, and then since D3's value is 0, let's put it into 1, and then next is we have 1, 1, 0. So because the original value here of C2 is 1, 0, 1, 1, 0, since D3 from 0 it becomes 1, and then this is the XOR operation. Okay, and then also the um, C4. So C4 is we have D2. So D2 is 0. And then D3 is 0. Let's make it into 1 since that's the error. And then 4 and 8 is we have 1, 0. And then, okay, so let's solve it. Okay, so we have to pair it again. Okay, 1 XOR 1 is equal to 0, 1 XOR 1 is equal to 0, and then 0 XOR 0 is again 0, and 0 XOR 0 is we have 0. And then next is we have uh, exactly in pairs. Okay, 0 XOR 1 is 1, and 1 XOR 0 is 1. And then 1 XOR 1 is equal to 0. So we have to write the original, we have 1, 0, 0, 0. And you have to read it upwards. Okay. So the check bit for the one that has the error is we have 0, 0, 0, 1. So we already have the two values. So what are we going to do here? So what we're going to do is we're going to XOR the check bit of the original word and the check bit of the word which has an error. Okay, so rewrite 0, 1, 1, 1, and then the operation is XOR, then 0, 0, 0, 1. Okay, so again, XOR is it's for have to it to have a value 1, the value should be different. So we have 1 XOR 1 is 0, 1 XOR 0 is 1, 1 XOR 0 is 1, and 0 XOR 0 is 0. So we have 0, 1, 1, 0. So 1, 2, 4, 8. So 4 plus 2 is we have um 6. So since, is it correct? So yes, because the error happened in bit position number 6. So the error is in bit position 6. So that we have already proven that the error is in bit position 6 because the answer here is 0, 1, 1, 0. So for you to have another um, example. So let's have an example. What if, okay, what if the error is not in D3, but, example, another is in D8. Okay. The from 0 it also becomes 1. And then, of course, since this is single error correcting code, let's assume that D3 does not have an error. Okay? So in D12 or in bit position 12 or data bit D8. So what if the error is in, so another example, the error is in D8. Okay, again, we have to get the original um check bit since we already have the original. So this is the original, this part. So we have 0, 1, 1. And then let's see which of the check bits C1, C2, C4, and C8 is affected by D8. Actually, it is C4 and C8. Okay, C4 and C8. Okay, so let's see. Let's recompute C4. Okay, C4 is, we have D8 is both on the last. So let's just change its values. So actually, that's the easy part with Hamming code and also for error correction in computers because their values are only zeros and ones, not compared to our number system, which has 10 distinct numbers from 0 to 9. So it's easier to detect errors because the computer only has two values, which are binary values 0 and 1. So let's get back again. So for C4, so we have, let's copy the original 0, 0, 1, and then since that's the original value, we'll do it into 1. Okay? Then the operation is also XOR. And then another is we have C8. Okay, C8 is we have 1, 1, 0, and then here is D8. So let's change also it into 1. Okay. Okay, so again, pairwise for XOR. 0 XOR 0 is 0, 1 XOR 1 is 0. So the value here is we have 0. And then next is we have 1 XOR 1 is 0, 0 XOR 1 is 1. Then 0 XOR 1 is equal to 1. Okay. And then let's write again the original values. So we have from C1, C1 is what? C1 is 1, C2 is, okay, wait. C1, then C2. C2 is also 1. And then the change value of C4 is we have 0. And then C8 is equal to 1. And then read it upwards. So the value or the check bit for the word that has an error in D8 is 1011, and then just the previous with the error is in position 6. So the original check bit is again 0111, and then you need to XOR it with 1011. So XOR. Okay. So the symbol actually of XOR is a plus sign and then a circle. So again, XOR, the same value 0, different values 1. So we have 0, 0, 1, 1. So since 1100 is 1, 2, 4, 8, 8 plus 4 is equal to 5. So it means we have already proven that the error is in bit position 12. So, so that is the tutorial for Hamming code for single error correction. So again, to solve for Hamming code is you should have the word, and then you have to count how many digits there is for the word, and then also what specific data bit position has error. So for bit position you have to create a table, and then this bit position number, it's useful if you do not memorize the values in binary, and then have to label first. It's safer to label first the check bits, which is the powers of 2. For this example, we have C1, C2, C4, and C8. And the remaining values are, we have in data bits. And then after that is we have to get the check bit of the word without error by getting for C1 um, data bit positions with a value 1, and then C2 with value 2, then C4 with value 4, and C8 with the value 8 in binary. So that's why we have this formula. Actually, this will be the same for 12 digits. So that's why you can memorize, but of course for memorization, if you're not good in memorization, it's better to derive. Okay, there's no problem if you want to derive, or if you memorize it, as long as the one that you've memorized is correct and it will never be wrong. Okay, and then after that is of course you have to XOR all the data bits. So again, XOR is should be done in pairwise. You cannot do it by threes or by fours. You have to do it in pairs. So this will be the values, and then you have already gotten check bit of the word that does not have an error. And then next is um, get the check bit of which this has an error. But as I've said, for the first example, the sub 3, the only um, check bits in the table that is affected by D3 is C2 and C4. So that's why in this example, I only um, recalculate C2 and C4. And then, of course, we don't have to, please don't forget the original values of C1 and C8, of course, in proper order. So that's why when I wrote it, so 0001, and then getting the check bit of the word which has a single error, we have to XOR it with the check bit of the word that does not have the error, and then you will get 0110 for this example, which is if we're going to convert this, we have 4 plus 2, we have 6. So we have already proven that the error is in bit position 6. And then the same goes with the error is in D8, which is in bit position 12. So I hope that you've already understand how to do the Hamming code for single error correction. So I hope that you've learned a lot from this lesson. So I hope that you won't forget to subscribe and also like this video and subscribe to my channel. So thank you very much. Good day and stay safe, and see you for another tutorial about computer organization and architecture.